In last video, we have discussed the conditions we need to know to identify Euler path and circuits. In this video, we will focus on Hamilton path and circuits, and we will take some examples so we can understand such difficult problem. So first, let us take a definition. A simple path in a graph G that passes through every vertex exactly once is called a Hamilton path. And a simple circuit in a graph G that passes through every vertex exactly once is called a Hamilton circuit. By mathematics, we mean by this that the simple path x0, x1, up to xn in the graph G is a Hamilton path if V is a subset of the set x0 up to xn, and the condition that we need to make sure of is x of I not equal x of j for all the values of I greater than or equal 0 and less than j and less than or equal n. And the simple circuit x0, x1, xn minus 1 up to xn and then go back to x0 with n greater than 0 is a Hamilton circuit if x of 0, x1, xn minus 1 and xn is a Hamilton path. This terminology comes from a game called the Hamilton puzzle, invented in 1857 by the Irish mathematician Sir William Hamilton. It consisted of a wooden dodecahedron, which is a polyhedron with 12 regular pentagons as faces as shown in figure 1, with a peg at each vertex of the dodecahedron and a string. The 20 vertices of the dodecahedron were labeled with different cities in the world. The object of the puzzle was to start at a city or node and travel along the edges, visiting each of the other 19 cities exactly once, and end back at the first city. The circuit traveled was marked off using the string and pegs. In figure 2, we need to start at any node, let's say B, and visit all nodes by traveling each edge exactly once. Try to think which path is the best one to solve what is called Hamilton's puzzle. Is there a circuit in the graph shown in figure 2 that passes through every vertex exactly once? Finding the answer to this question, it solves the puzzle because this graph is isomorphic to the graph consisting of the vertices and edges of the dodecahedron. So a solution of the Hamilton puzzle is shown in figure 3. To clearly understand Hamilton path and circuits, let us take the following example. Which of the simple graphs have a Hamilton circuit, or if not, a Hamilton path? G1 has a Hamilton circuit, and this could be A, then B, then C, then D, then E, and then A as shown in figure 5. There is no Hamilton circuit in G2 as shown in figure 6. This can be seen by noting that any circuit containing every vertex must contain the edges A and B twice, but G2 does have a Hamilton path, namely A, B, C, and D. G3 in figure 7 has neither Hamilton circuit nor a Hamilton path because any path containing all vertices must contain one of the edges A and B, E and F, and C and D more than once. Is there a simple way to determine whether a graph has a Hamilton circuit or path? At first, it might seem that there should be an easy way to determine this because there is a simple way to answer the similar question of whether a graph has an Euler circuit. There are no known, simple, necessarily, and sufficient criteria for the existence of Hamilton circuit. However, many theorems are known that give sufficient conditions for the existence of Hamilton circuit. Also, certain properties can be used to show that a graph has no Hamilton circuit. For instance, a graph with a vertex of degree 1 cannot have a Hamilton circuit because in Hamilton circuit, each vertex is incident with two edges in the circuit. Moreover, if a vertex in the graph has degree 2, then both edges are incident with this vertex must be part of any Hamilton circuit. Also note that when a Hamilton circuit is being constructed and this circuit has passed through a vertex, then all remaining edges incident with this vertex, other than the two used in the circuit, can be removed from consideration. Furthermore, a Hamilton circuit cannot contain a smaller circuit within it. Show that neither graph displayed in the figure has a Hamilton circuit. There is no Hamilton circuit in G because G has a vertex of degree 1, namely E. Now consider graph H. Because the degrees of the vertices A, B, D, and E are all 2. Every edge incident with these vertices must be part of any Hamilton circuit. It is now easy to see that no Hamilton circuit can exist in H, for any Hamilton circuit would have to contain 4 edges incident with C, which is impossible. Show that K of n has a Hamilton circuit whenever n greater than or equal 3. Now figure 9 is showing some example of graphs K of n for n greater than or equal 1 and less than or equal 6. So we have K of degree 1 and K of degree 2. We need to prove that any graph of degree K of n has a Hamilton circuit. We can form a Hamilton circuit in K of n beginning at any vertex, such as circuit can be built by visiting vertices in any order we choose, as long as the path begins and ends at the same vertex and visits each other vertex exactly once. This is possible because there are edges in K of n between any 2 vertices. Now this leads us to conclude the following theorem. Dirac's theorem: if G is a simple graph with n vertices with n greater than or equal 3, such that the degree of every vertex in G is at least n divided by 2, then G has a Hamilton circuit. The other theorem, Oris theorem: if G is a simple graph with n vertices with n greater than or equal 3, such that the degree of U plus the degree of V greater than or equal n for every pair of non-adjacent vertices U and V in G, then G has a Hamilton circuit. Dirac's theorem can be proved as to the Orius theorem because the conditions of Dirac's theorems imply that of Orius theorem. Both Orius theorem and Dirac's theorem provide sufficient condition for a connected simple graph to have a Hamilton circuit. However, these theorems do not provide necessarily condition for the existence of a Hamilton circuit. For example, the graph C5 has a Hamilton circuit but does not satisfy the hypothesis of either Orius theorem or Dirac's theorem, as the viewer can verify. Hamilton paths and circuits can be used to solve practical problems. For example, many applications ask for a path and circuit that visit each road intersecting in a city, each place pipelines intersect in a utility grid, or each node in a communication network exactly once. Finding a Hamilton path or circuit in the appropriate graph model can solve such a problem. The famous traveling salesperson problem, or TSP, also known in older literature the traveling salesman problem, asks for the shortest route a traveling salesperson should take to visit a set of cities. This problem reduces to find a Hamilton circuit in a complete graph, such that the total weight of its edges is as small as possible. So figure 9 is showing an example of such interesting problem as we are going to discuss in next video. Thank you for watching.